Okay, college algebra, let's talk about different kinds of transformations. Now that we've done piecewise functions, it's time to learn how we move from basic functions without having to plot every point. So attributes of functions, stretches and shrinks, reflections, and shifts. So if you've got a number multiplied in front of your function, a times f of x, and that number is greater than 1, it creates a vertical stretch. If it's a fraction, it creates a vertical shrink. So something like, if I have the square root of 2, or f of x equals the square root of x, if I take something like f of x equals 3 times the square root of x, it stretches the graph. All the y values get tripled, so instead of the square root of 1 being 1, we now have the square root of 1 equals 1 times 3, so we're at 1, 3. 4 is now at 6. For example, the square root of 9 is 3, but now it's at 9. So it's tripling all the values. So what does it actually do to the shape? It is stretching it upward, so pulling it upward. Now if you've got a fraction, like f of x equals 1/3 square root of x, instead it will shrink it. So instead of 1, 1, we have 1, 1/3. Instead of 4, 2, it's 4, 2/3, and 9, 1/3. So it's like flattening it from the top. So the idea here is that number in front of the whole function is a stretch or shrink in the vertical direction. However, if the number is in front, is a stretch or shrink in the horizontal direction. So what does that mean? I have an absolute value function on here. It's not the greatest example of this, but if you take something like the square root of x, and instead it's now the square root of, say, 2x, then that is a horizontal stretch. In this case, this function is right now the square root of x plus 2 plus 2. If I replace x with a 2x, then we have, it's kind of a shift. That was a bad example, but if I take 2 times the x plus 2, so 2 times everything on the inside of the function, it will horizontally shrink, which looks exactly like a vertical stretch. So what happens here is, in the case of an absolute value, it actually looks exactly like a vertical stretch, the horizontal shrink, because if you, visually, if you have a grid like this, let's talk about a square. If I double the height of a square, it becomes a rectangle. But what if I squeeze the width and cut it in half? It still becomes a rectangle. They're the same shape, just one of them is bigger, but if there's a field of view and these things are going on forever, it doesn't look any different. So sometimes for vertical stretches and horizontal shrinks look the same depending on your kind of function. However, for say the absolute value of x, or I mean the square root of x from above, if this is the regular square root of x, a horizontal stretch, the ratios may look different. Cube roots could look a little different, but most of the time, a lot of our functions, because of the way they behave, will look similar. A horizontal shrink and a vertical stretch will look the same. Similarly, a horizontal stretch and a vertical shrink can look the same as well. Where the graph is kind of pulled apart faster, it looks the same as it was being flattened. And you notice we talk about this, I say horizontal stretches make the graph look wider and shorter, and then vertical shrinks make it look shorter and fatter, which really means the same thing. But they just kind of have opposite effects. So the horizontal stretch and a vertical string could do the same thing. So those are for stretches and strings. And usually the stretches and strings are either the whole functions multiplied by a number or just the x values multiplied by a number will have an effect on it. It can also affect the center, but we'll talk a little more about that in the order in which we apply things. Now the other thing that can happen is reflections. You notice that absolute value was facing down because I put a negative in front with the front of the whole equation. Reflecting across the x-axis changes the sign of all the y values. So if you take a whole function and multiply it by a negative, you'll notice on the last page we only talked about multiplying it by numbers that were positive. If you multiply it by a negative, it changes the direction. So instead of an upward-facing parabola, of course, negative x squared has a downward-facing parabola. So we take the original and we link it to the next one. Here's the original y equals x squared. Here's negative x squared. Now if we talk about it reflecting y values, let's talk about what that means from a domain and range standpoint. Normal x squared goes from 0 to infinity. But if I am reflecting the y values, I'm also reflecting the range. So I take the opposite signs of each of these, that's negative 0 and negative infinity. The order needs to change, but negative 0 is still 0. So not only does it reflect it across the axis, it also reflects the range. Reflecting across the y-axis changes all the x values. Now changing all the x values reflects the domain. So if I take the square root of x and change it to negative square root of negative x, the only numbers we can put under the square root are non-negative. So there's a negative multiplied there. The only things we can put in is negatives or non-positives to turn negatives. So this reflects across the y-axis, and notice that it shifted the domain from only the positives or non-negatives to only the non-positives. So that's what negatives do, and this is if the negative is attached to the x on the inside. Now because of all these types of reflection, we have a few types of symmetry. Symmetry about the x-axis means that when you reflect it across the x-axis, it's the same shape, which means, we said last time, that's putting a negative in front of the whole function. That means f of x has to equal negative f of x, so when you reflected it, it didn't change. Symmetry about the x-axis is almost never a function because it requires you to have one x value going to two y values, which is the textbook definition of not a function. The only line that is a function here that is technically symmetric about the x-axis is the line y equals 0. About the y-axis, when you can reflect left and right, and the functions be the same, f of x has to equal f of negative x. These are called even functions, and that's because x to any even power is an even function. Symmetry about the origin is when if you reflect it across the x-axis and y-axis together, or you rotate it 180 degrees, it's the same function. So that's where f of x equals negative f of negative x, and these are called odd functions. All odd powers of x and odd roots are functions. Let's talk about y equals x squared, which we know to be the parabola. What kind of symmetry does it have? Is it reflectable across the x-axis? No, it'll be different. Y-axis? Yes. So it's got symmetry about y. Does it have symmetry about the origin? No. In order to be symmetric about the origin, you have to be symmetric about both y and x, or neither. So this is the only one it has. X squared plus y squared equals 1 is a circle with radius 1. This is symmetric about x, because you can flip it up and down. You can flip it left and right, so it's symmetric about y. And if it's symmetric about both x and y, it's automatically symmetric about the origin. It's not a function, which is why it's allowed to be even and odd. And lastly, the cube root of x. We've seen this before. It's like the flat-lying s. It's not symmetric about x or y, but it is about the origin. And we'll continue in the next video.